So I'm Chang, and yeah, I did a lot of data center networking stuff for maybe 5-6 years, and then felt that I did a lot of things that I could do, but there are a few things that I couldn't do, even if I owned the data center networks. And and the reason why I couldn't do those kind of things is because I didn't have something like P4 or P4 targets. And I heard about this, and then it just sounded so exciting. That's why I moved. So let me quickly go through this agenda. So this morning, I'm going to give you a very quick overview of P4, along with motivation and how it works and so on. And then we're going to have a lecture session led by Vladimir. Vladimir actually led a similar kind of teaching or education sessions for other high-speed chip targets, and so he's very well experienced, coming with a lot of expertise in the field, so it will be very helpful. And then in the afternoon, we're going to start with the lab session. So we prepared two fully sort of designed assignments: source routing and flow lab switching. And we'll solve these problems together with you. We'll do this coding together with you so that you can actually finish these two. We also have 2 or 3 other half-baked assignments, meaning that we haven't solved this entirely yet. We don't have a full solution or a test framework, but we have rough ideas, and we're quite sure that you strong students like you will be able to solve these problems maybe in an hour or 2. Okay. So we'll introduce them, and then I encourage you to tackle those assignments as well. And then we also have a panel for the end of the afternoon, and then we have a dinner served at a nearby restaurant here, so that we can meet together and then meet with other people, either panelists or maybe some experts in the field in shared networks as well. Tomorrow is mostly interactive session, so we could have prepared even more assignments, but we felt that that's a little too much. We really wanted to make this tutorial as interactive as possible and helpful to you, especially to your own research agenda. So we highly encourage you to talk about your potential P4 assignments or your research topics that are related to the P4 language. But it could be either P4 new use cases of P4, or it could be the language extension itself. Okay, I felt that P4 is a little weak on this side. I wanted to improve on that. That's totally fine. Or it could be related to the tools part. Right? I think P4 is great, but I didn't see this particular kind of tool that I badly wanted, and I wanted to discuss with you so I can actually conceptualize, design, and even prototype it with you, and then contribute it back to the P4.org. Anything is fine, so I want you to share those kind of ideas with us so that we can help and work with you, and then we reserve the entire morning actually to work with you on your projects. And then in the afternoon, we'll start a talk by originally Mihai Budiu. Mihai is working for Barefoot, formerly worked for Microsoft Research here, and then he did a lot of important language and compiler and distributed systems work, including Dryad. If you have heard about Dryad, that's basically attributes that Microsoft is using for their internal architecture systems. And he actually developed the language for Dryad. But unfortunately, Mihai had a family emergency, so he had to fly back to Romania yesterday. He had a loss in his family, but he left his material, so we're going to ask another expert, Chris, to lead these sessions. And then finally, we'll have a presentation session. So you will have maybe 15 minutes, 10 to 15 minutes each to talk about what you have worked on throughout this session. It's okay. I mean, we understand that you don't need to come up with a complete presentation or very well-versed presentation. It's just brainstorming, right? Hey, I thought about this problem throughout this tutorial, and I went up to this point. Seems like the remaining work items, this. But if we get this done, it seems like we can solve these kind of important problems. Just that level is totally fine. So we'll go through this and then ask you to present your ideas and then share the feedback, or sorry, share the ideas with us. And more importantly, you'll be able to get the feedback from other students as well as me and Nick. So Nick will actually join this session end to end so that he can also share his feedback with you. Great, and then after tomorrow dinner, so we'll prepare for the dinner here on site. But we'll open this garage for another maybe 2 or 3 hours. So if you want to, hang around and then do more, discussions or coding work or brainstorming with us or other students, that's totally fine. We're encouraging you to do that. We're going to actually call it a party, so we'll have maybe some beer or whatever. I hope that everybody is old enough to be able to consume alcohol, right? If not any students, right? Okay, good. Any questions about the agenda? Okay, great. So let's get started. Vladimir, is this
What?
remote for this one? I see 2. Which is which? Okay. And this is this one. Just one more comments about the CLA that Nick talked about. So, as I said, or as Nick said, the decision on whether you're going to make any contributions back to the language consortium or not, that's totally up to you. We're not asking you to do anything. But the reason why we're asking you to do this is that contribution can be really minor thing, but we still have to get your signature. For example, you found a bug, maybe in our compiler or some open source code that P4 Language Consortium maintains. If you want to come up with a pull request and then send it back to us, we'll have to ask you to sign that NDA or CLA, and maybe some suggestions for the spec language. Even for that, we'll have to get your signature, consentment. It's just legality issue. Otherwise, we can't take your contributions at all. That's why we're asking you to sign that. And we're not asking this only to you. Anybody who's contributing to the language consortium, we're doing this. It's part of the legality. Okay. Good. So I have prepared a brief presentation, but it seems like you might have been already primed with this knowledge. So, well, actually, it seems like it's a mixture.
Just raise your hands
Yeah.
if you feel comfortable with before, did something with before already. Okay, so looks like you can go.
I'm interested in hearing this.
Sorry, what?
I'm interested in hearing this.
Okay. So,
Yeah.
I'll try to,
Go ahead.
yeah, I'll try to make this within maybe 20 minutes and then see how it goes. Okay. So, this is all about programming the data plane, not control plane. So today, you wanted to build your own switches, doing something special or doing just regular things, L2, L3, whatever. This is how it works. You have your own fixed function chips, either your own in-house developed chips or maybe merchant silicon chips are available out there. Either way, you somehow figure out how this chip works by reading thousands of pages of reference or materials, or by talking to their architects, or by somehow. If you're big enough like Microsoft, Google, you may be able to pull a lot of strings and then merchant silicon vendors will be happy to talk to you. If this is your in-house solutions, you have a little more resource, but still you have to learn how this works. And then you write your own switch control program, your routing protocol daemon, your protocol stack, your driver, any software components that run on the switch, and then this switch start functioning correctly. There are two problems in this process. First of all, this is done in English. And of course, the design of this is done, machine language may be very low or something like that, but software engineers cannot understand millions of lines of very low code, or maybe RTL is impossible to understand, right? So it's impossible to understand exactly how this chip behaves under circumstances. Second, this is fixed function. So if you want to introduce new functionality, however trivial or however significant it is, you have to wait 2-3 years, hopefully. And as a result, this causes two big problems. First of all, prone to bugs, meaning that this understanding is actually not precise at all. There could be a lot of misunderstandings. Human language-based conversation, specs can go only so much, right? You have to read the programs to see exactly what's happening. And you have to run the programs and then test the programs to understand how it works. And very long and unpredictable lead time. You want a new feature, wait 2-3 years, biting your nails. Usually they don't come on time, and then when they come, they're not exactly coming in a fashion that you asked for. Like, hey, I wanted X, they delivered X dash, and then that dash might not be trivial oftentimes. So even if we lived in this world, if the networking world was stable enough, it might have been okay. Unfortunately, networking is still changing. My own experiences, so network virtualization was something that I did in Microsoft. We started with VXLAN or NVGRE, and then soon after, people felt that, hey, we need extensions to these relatively new protocols. And people came up with STT and VXLAN GPE. And yet, as if those were not enough, we're talking about NSH and Geneve, new sets of protocols keep happening. Yes?
So why do we need so many new encapsulation protocols? What's the motivation?
That's a great question. Because everybody has slightly different requirements. For example, VXLAN originally started with this 8-byte long fixed header, and then people thought that, hey, I wanted to attach more options, or I wanted to reuse some of the reserved field to deliver some more information. STT, it's TCP based, sometimes, right?
It predated VXLAN actually.
Oh, does it? Yeah. Actually. Okay, good. So VXLAN is UDP based, and then people thought that for TCP you can actually offload some of the features to the NIC if you manipulate those kind of things well enough. So they wanted to use TCP-based encapsulation. NSH, Geneve, people want to attach any data in a TLB type length value style fashion. So they thought that, hey, once we have encapsulation, we can attach even more information there. So it's still evolving. OpenFlow, you have seen this, right? Started with a small number of well-defined fields, and then it keeps growing and growing. Right now it's 44 fields. Who knows where this is going? So everybody wants their own specific features. Everybody has opinions. So why can't we just let them do whatever they want, and then we can just get away from their way? That's the ideal labor of division. But if you think about this industry carefully enough, we've been having some programmable chips or programmable solutions at least. For example, CPUs, of course, although it works at tens of Gbps range. We also have FPGAs and MPUs which work at hundreds of Gbps today. But there is a new type of chip coming up, which we call PISA architecture, protocol independent switch architecture. And it claims that it can actually handle a few terabps of traffic with enough programmability. And we have seen this paper, R&D paper, and a few emerging solutions. They're from, Cavium is talking about their programmable multi-tier VPS solution. It seems like a few other companies are also working on that. So essentially, this is a merchant silicon with fully programmable parser and generic match action logic. There is no built-in knowledge of particular protocols at all. Then we predict that this is going to be the dominant types of chips that will be delivered, produced, and consumed within a few years. And therefore, we have this new word. Programmable device. Now, you dictate the behavior first. So this is the first step that you do. And you say that this is precisely how you must process packets. And then you write your own program, and then that just works as it used to be. And this is done by a new language called P4. So it's not anymore human language based. So what does this mean? So it could mean a lot of different things to different types of parties. To network device vendors, if you're delivering your own systems, such as you invented your Arista or Cisco, then it means you can apply your software programming practices and tools in every phase. So far, there's strict hardware development tools and phase, and then there is software development phase. Software takes care of only the software, and hardware is just done by a totally different process. Now, if you use P4, you can develop your hardware or data plane logic in software. So this will allow extremely fast iteration and feature release, because it's a matter of rewriting or changing your P4 code rather than rewriting your parallel code and then doing physical optimization and all those hardware development things, which takes months and years.
So, sorry, I wanted to understand that. Is that because you would take the specification and compile that down to the Is that the reason why you can?
When you do the hardware development using Velo, yes.
Okay.
Okay, so you can also differentiate capabilities and performance. Even if you're using merchant silicon, because this merchant silicon is now programmable, you can realize your own idea, and then your competitor who are using the same merchant silicon might not have understanding on this idea, right? So you can still differentiate. And then finally, they can also fix data plane bugs in the field. Not all data plane bugs, but some data plane bugs which are caused by the bugs in your P4 program or your compiler. Those things are fixable. To large online service providers, mainly the consumers of this kind of chips or networking solutions, this means that they don't need to worry about the black boxes, the big black box module in their white box solutions. So because they can't control the behavior of this chip, there's no real black box anymore. And then their developers, they have armies of developers. I mean, that's their core capability, right? Their developers can now program, test, and debug their network devices all the way down to the way these packets and bytes are shipped over the wire. And that's directly connected to the visibility argument that Nick talked about. I don't want complicated behavior. I want it to simplify, but I want to make sure that I understand every single detail what's going on in my network at the device level. And then finally, they can keep their own ideas. Right? Google, Microsoft, Amazon, Facebook, today they're all using the same merchant silicon chip. So even if you're powerful enough, you convince that merchant silicon provider that, hey, you have to ship this particular feature. Once they ship, it goes to everybody. My feature shared with my competitors. In the P4 world, they don't need to, because they're not talking about particular features with the silicon provider. With the silicon provider, they're talking about programmability, language, and then more table and less table, more pipeline stages. They're talking about that level of requirements rather than individual features. So why do we call this protocol independent packet processing? Mainly because these programmable chips or devices do not understand any protocols until they get programmed. So this is a conceptual diagram of the PISA architecture. So programmable parser at the ingress, multiple stages of match-action pipeline, and then the queues. You could also have the egress, sequence of pipelines as well. The key point here is that this is programmable, and second, this is identical. Every single stage is exactly the same as the other stages, and therefore no protocol knowledge here. So when a packet comes in, it gets parsed, and then the parsed representation goes to the first stage, and then the second packet comes in, gets parsed, and then it keeps moving on. Okay, and actually Lisa contributed to this diagram, right? Okay, so now this is the physical pipeline, and then you, as the owner of this network device, describes your logical data plane behavior, and then that's done in P4. So this is your P4 program, just graphical visualization of that. So you want it to L2 lookup first, and then depending on the packet types, you want it to like V4 routing or V6 routing. Finally, access control list. Okay. So then you compile this, then the compiler will take care of the actual logical to physical mappings, taking into account all the constraints subject to this particular underlying architecture. Okay. Yes?
So the assumption for the PISA architecture is one in which you can move forward through the pipeline, but you can never go back or loop around inside it.
So it depends on the architecture. The spec actually says that recirculation path may be available, but recirculation can come at cost, right? If you recirculate packet, it means that you're losing the cycle that would otherwise be used to serve other packets. So your effective throughput may go down. But that's a target specific trade-off, right? Some targets might not have such trade-off.
And the recirculation features at the granularity of going through an entire pipeline and then getting directed to go back into that pipeline or a different one, or within a pipeline can you
yes,
move
so that's
backwards
yeah, that's what the spec currently says. In addition to recirculation, there is resubmit as well. Resubmit means that the packet goes through this, and then it's not actually coming back. You just simply restart it. So typically, when you talk about this kind of architecture, it's not the actual packet that travels. The packet comes in because packet is large. Only the parsed representation actually goes through this process, and then the packet is actually sitting somewhere else, cell-wise fashion or something like that. So you can just simply decide to reparse it along with the metadata produced through the first pass. So we distinguish between resubmit and recirculate in the spec. Yes.
So if some targets do not have recirculation, then
Yeah.
it means that the stages that they go through, the
Yeah.
number of stages is
Yeah.
fixed, right?
Yeah.
But the number of stages is you cannot determine it before the compilation, right?
Yeah.
So what if after you compile it, you find out we have more stages than the targets?
So then you have to go back and then change your P4 program. Right. It's like running out of memory. So it's like you can think of it as very system dependent compilation process. It's like compiling your kernel to particular CPU logic. Right? But the one thing that I wanted to make a note is that the number of dependencies or the depth of dependency chain that you can see on this logical data plane view might not actually necessarily identical to the number of physical stages you need, because typically human beings do not understand the dependencies carefully enough. So when you actually compile, oftentimes you actually see the target using much less number of stages. So the compiler can actually identify parallelizable tests quite well, and so the actual consumption in number of stages that you use might not actually correspond to this kind of, the depth of your graph. Okay, so compiler takes care of this logical to physical mapping based on the understanding of the dependencies in your P4 code as well as the constraints in this physical pipeline. And the constraints mean table size or number of ALUs available and all those things. So now, suppose you wanted to change your logical data plane behavior by, for example, inserting a new encapsulation protocol between layer 2 and layer 3. So you decide to your own layer 2.5 encapsulation. Okay? And you change your P4 program, and you might also need to change the size of one of the other tables, because even without this, you are using your physical memory entirely. Right? So you set the size of these things based on the understanding of the physical pipeline or the compilation result. Now, if you introduce a new table, you might have to cut somewhere else. So you decide to cut IPv6 size a little bit, and then you compile it again, and the compiler will again take care of the new mappings.
So is the size something that's also specified in the like for each?
Yeah, it's one of the things that you want to dictate, right? Of course, there could be different modes, right? You say that, hey, the size, I don't care about the particular size. I want minimum size or I want maximum size. There could be different options, but in general, size is something that you want to dictate as the owner. I want this much of capability for my B6 and B4 and so on.
What is the typical size of the table that depends on you?
At the logical view or the physical view? That's totally target dependent. Yeah. So we may be able to share the numbers for our target, Barefoot's target on Saturday, but typically it's target dependent, and then the compiler should come with that target, the back-end portion of the compiler, primed with all these specific constraints and knowledges of the targets.
So the user has to see the numbers.
Yeah. You assume that user has reasonable understanding on the physical limitations, but it's an iterative process, right? You start with something, you compile it, and then compiler will give you a pretty good visualization or output, saying that, hey, you're actually leaving a lot of resources. You're not maxing out this capability. Then you go back to your programs. Oh, I have a lot more memory, so I'm going to increase the size somehow, or the other way around. So what does a P4 program look like? It's very simple. You just need to identify the actors, meaning the headers. So Ethernet, 9-cap, P4, V6, TCP, UDP, and then the definition is very straightforward. If it's Ethernet, header type, and then all the fields in the header, and then the length of the field in bits. Then, if you want to do your own header, you can define your own header. The next step is interconnecting between these headers, basically expressing your parse graph. And parse graph is basically transition or state machine. So you define states and then define the transition conditions between these states. So that's what this parser language does. So each one of these, starting with parser, is defining a state, for example this state, and then you extract the header, the particular header, Ethernet in this case. Then based on some values that you have extracted, you dictate the next move. And then if you wanted to do some IPv4, more realistic header definition, you can see that you can actually dictate the something like this as well. So variable length fields are also supported. The next step is now defining the table. You have defined headers and then header extraction parse graph. Next step is defining each one of these logical tables. So let's look at IPv4, for example. Read defines the keys that you want to use to look up this table, logical table. And then actions is for each entry in this table, you will attach that entry to a particular action. So you could actually specify multiple actions here. Doesn't mean that each entry runs multiple actions. Each entry will be associated with one of these actions. So in this case, you're using only one key, and then the lookup semantics is LPM. You could define multiple keys, and then each key can have its own match type: LPM, exact, valid, ternary, range. Those things are all supported match types. So conceptually, what this means is, as I said, you're defining the table framework. This is the key, and this is the lookup semantics. And then each entry in this table that I'm going to populate later at the runtime. So table population is not done at the compile time. Compile time, you just define the table so that the compiler can leave or reserve enough resources to be able to host this table. And then at compile time, runtime, you'll be populating or depopulating this table through your own protocols. So when that happens, you will associate each entry that you add into this table with one of these actions. And then these actions are entirely custom defined, built on top of the primitive actions or action macros. So these are essentially, these both things, which we call primitive actions, are something like instruction sets, unique to the particular architecture. And then of course there is a standard set of primitive actions defined in the spec. So modify field, add header, remove header, copy packet, and all those things are available. So you define your own compound action. So this is the name that you come up with. And then the set of parameters is also your defined, custom defined. And the body of this is again custom, but it should be built with the primitive actions. So this particular action, for example, set next up, you define this action this way. So roughly, you basically get the next up address and port number at runtime from the runtime system, and then you copy this parameter value into this metadata, and then you decrement the TTL value by 1. That's what it does. Yes?
So if you have multiple fields that you're matching against in the read,
Yeah.
then each of those are in the entry, are each of those fields in one entry on the table?
In a concatenated fashion.
In a concatenated
Yeah,
fashion?
yeah.
But if one's like longest prefix match and the other one's exact,
Yeah.
then those require like different types of lookup, right? So
Yeah.
one's TCAN,
Yeah.
one's binary.
No. It's the compiler's choice.
Okay.
So, but reasonably, what most compiler will do is that, because at least one of these keys is ternary, I can't use SRAM.
Okay.
I'll have to use TCAM. Unfortunately, although the other fields are exact, because one of them is ternary or LPM, you'll probably put the entire table into TCAM.
Okay.
So it's compiler's choice. Yes.
So when the semantics goes from parallel to sequential, right?
Yeah.
It means that each instruction goes in order.
From your understanding.
From my understanding.
Yeah. From user's understanding.
Am I allowed to modify the same field twice in the same action?
You can do that, although some compilers may reject that. Some compilers may detect that, this guy is introducing dependency or some collisions. And if the target can actually support a very long or arbitrary depth of dependency chain, it may not complain. It will take it. For example, software router can do any depth of dependency here, right? It's just too slow. Whereas if it's hardware target, it will probably has a certain limit to the dependency chain. Then its compiler will detect that problem. If you happen to violate in your definition, then it will give you compile time error.
So is the compiler able to see that from the intermediate representations?
Yeah. It has to. That's very important. Yep.
So 2 questions.
Yes.
The first, in the table, you only need to specify what's being read, not what's being written.
Yeah.
In terms of the fields. Those can be inferred from the definition of the actions.
So could you repeat? Yeah.
So you specify which fields are being read, but the actions
These are
will
the keys.
write
Yeah.
certain fields. So you only need to specify the keys.
Yes.
But all the rest of the headers available for manipulation.
Yeah.
Okay.
And as well as metadata.
As well as the metadata.
Yeah.
And the second question, yesterday you had mentioned modify field with expression
Yeah.
as the new way of doing things. So is this
Yeah.
add the field with deprecated?
No. This is still available, but what I'm saying is that this can take now an expression, not just one field or metadata. You can take multiple field or metadata combined by some operators
Okay.
as a source.
So like you could do potential negation?
Yeah.
Okay.
Okay.
One more question.
Sorry. Yeah.
Could you explain more about what is metadata and what is standard metadata in doing something?
Yeah. So there are two types of metadata: intrinsic metadata and user-defined metadata. Intrinsic metadata is target dependent. Although there is a standard set of intrinsic metadata that we're saying that every target has to support at least this set of metadata. So intrinsic metadata has something to do with hardware. It's either generated by the hardware or it's consumed by hardware, and then it's like control register in compute world. If you set particular value to this particular intrinsic metadata, somewhere down the pipeline, say for example TM or parser will understand it and then do something specific. User-defined metadata, both the source and consumer, provider and consumer are you, the people program. So you define your data, carry it along, and then somewhere down the pipeline you use it.
Sorry.
Yeah.
Language is very good.
Yeah.
So the reads have a field
Yeah.
defined
Yeah.
which
Yeah.
reads your reading. So
Yeah.
symmetrically, like for the writes, for the actions, we don't actually say.
No, this is not the best choice of language. You can just say that it's keys. These means keys. The keys of this table that you're going to use to look up this table, it is the series of this one. That's what it means.
Right, but so in the other case, you don't
Yeah.
actually say which fields are going to modify it. So is there a reason for that? Or just,
I don't quite understand.
so for the reads, you
Yeah.
actually specify like, which keys are going to be. But for the actions, for the writes, you don't
Yeah.
actually say in the table like, which fields are going to happen.
Your action body will dictate that. So in this case, these three fields are overwritten.
Okay, yeah.
These
yeah,
two
I guess.
metadata and this header field is going to be rewritten by this action.
Sure.
So finally, once you define all the tables and associated actions, you define the order. I want to let my package go through L2 table first, and then my encap, and then depending on some conditions, they go through either V4 or V6 table and then the echo. So that's what we call control flow. So that's it. Now imagine that you're building your own new complete protocol, say not my virtualization. That network virtualization protocol has roughly three components. Right? First one, tenant isolation logic. It's really high-level policy. And second, your P4 program, basically the extension to the P4 program, introducing new table, myincap table, and then the header format of that myincap protocol. That's the P4 program portion. And then you also need table population logic. How am I going to populate this myincap table? There must be some logic for that, right? So only this portion is written in P4. The other two portions are still something that you've been doing in your software using your own choice of programming language, C or whatever. So this logic is basically composed of three pieces, or extension to the three pieces: parser, match-engine table, and control flow. And now let's see how this is actually mapped to the running switch. So you have your switch. That's typically a data plane chip plus CPU, which runs the control plane. And then the operating system almost always a variant of Linux. And then there is a switch chip driver through which the Linux communicates with the data plane chip. So you compile this P4 program, then it generates, one of the output is compiled forwarding logic. Right? So and this forwarding logic is loaded onto this chip at the boot up time or loading time. So this is a new path. With fixed function chip, you didn't have this path because this chip came up with its own protocol implementation already. So you didn't have this path. And then this compiler will generate another output, which is switch runtime API. Okay? And then you consume this API to populate these tables at runtime. So this is table population logic that you have written in C or whatever. This consumes the generated API. So these two pieces always go hand in hand. And the reason is obvious. If you introduce new tables, you need new SDKs or new API functions through which you can populate or depopulate these new tables. So they always go hand in hand. And then the fact that you actually auto-generate this API through the compiler is really powerful concept. Because it means that you own the SDK. It's not that you have to learn someone else's SDK. You dictate your own SDK. And then finally, this tenant isolation logic, that's just management logic that always runs on the CPU. So these two runs on CPU. And this data plane chip loading process.
Question.
Yes.
What's the difference? Can you go back to that?
Yep.
What's the difference between boot and init?
It's the same. Yeah. So sometimes when you boot, you may pick up the configuration, device configuration automatically. Sometimes you might actually want to init it explicitly, even manually. But that detach it from boot time. It's like field reconfiguration. I want to reinitialize this data plane chip with new compiled output. So the chip functions differently as well. Yeah, you basically recreate the chip. That's what I meant by unique. Yes.
Just to mention, so when you say table population, I assume it could be things like existing protocol, like BGP, OSP,
Yes.
or whatever.
Yeah. Yeah. Your own choice of protocol, either fully decentralized or logically centralized open flow style protocol, your approach. Okay.
More about tenant isolation logic.
That's just your policy. So this is control, management, and data plane.
Okay, so it's management part.
Yeah. So that's an example particular to this particular use case. Okay, so let's look at some demos here. Okay, so in this demo, I'm going to show you in-band network telemetry first. So you have seen a very short snapshot of this one yesterday. Mukesh from VMware actually gave this demo. So you write your own P4 program, and then you compile it. As I said, it generates two outputs. The first output is switch data plane configuration, and then the second output is the API. These two go hand in hand. If you had a real chip, this would be the configuration of, I don't know, millions or billions of registers. But right now, we don't have real chip. We're not using real chip for this demo. We're using the software P4 switch. So this is actually a generated C program. We're still using behavioral model version 1. So we use this, the generation approach for this demo. So generated C code gets compiled again, and then you have the binary. And then I load this binary multiple times so that I can run multiple identical switch processes. And then they're connected through virtual Ethernet interfaces. So it runs on Mininet environment. This API, auto-generated API, is consumed by my control plane script, which is nothing but just simple Python script. But I consume this API so that I can update the tables at runtime. So I built this network, again using Mininet. The default software switch in Mininet is OVS. I replaced that with our P4 switch. Okay. So I run 3 switches. Each switch is connected to one end host, and this is Linux. What is it? Yeah, just container or namespace that Mininet uses. And monitor happens to be just another end host, but I'm doing in-band monitoring. That's why I'm not creating a separate management or control network. So it just happened to be attached to switch number 3. So on this topology, I'm going to run a patch web server here and a web client here, and then I'm going to keep downloading the same web page from there to here, and then let's see what happens. I might have to reboot this machine, so why don't you take a short break? Please, instead of taking a short break, let me just continue the remaining of the talk, and I'm going to come back to rebooting this. Waiting for that.
So quick question.
Yes.
The P4 switches,
Yeah.
the control plane code that you have running, is
Yeah.
it running on those P4 switches, or is there some kind of control plane channel to them?
So the control API is auto-generated. That's either generated C API, or we also generate Swift-based IDL. So you can call it remotely using Swift. Right now I'm using Swift, but this control program is actually compiled with the data plane program. So
Okay.
it runs within the same process.
Okay.
But it's your design choice. You can completely separate them as two separate processes or even remote process. So let me come back to the demo after rebooting this. So this will accelerate innovations. Right? That's the main purpose. If you can modify things a lot faster, right? It took 3 years, now it takes 3 days. Literally. Writing your own people program, testing it, how long can it take? Maybe, okay, so let's be very, very conservative. 3 weeks. Right? 3 years versus 3 weeks. So, lots of areas of innovation. I'm just scratching the surface here. It will reduce, reducing feature set, as I said, or as Nick said yesterday. Not necessarily all the people are happy with all the protocol implementations available in the merchant silicon right now, because they're not using all of them. They can't possibly use all of them. For example, why would these large data centers use MPLS in their data center? And yet somebody out there wants it for whatever reasons, and then they have to be shipped. So that actually is, consumes a lot of space on the chip, either in terms of logic as well as cable. So people hate that. I want to use this chip as raw as possible, and I know that this has actually this much raw SRAM, this much TCAM. I want to use all these resources only to do whatever I want, whatever matters to me. So that's what I meant by reducing feature set. Network monitoring, analysis, and diagnostics. Because you run your own protocol, you can change the data plane, you can gather a lot of information. Tunnel splicing gateways. Whenever you introduce public to virtual interface points, edge devices, public protocols are relatively well known. Whether you like it or not, you have to do something. Private, they have different protocols usually. So this conversion, if you want to make that happen using merchant silicon, it means that you have to share your private protocols with that hardware vendor. If you don't want to do that, you're stuck. But with programmability, these kind of things are way easier. Load balancing, either dynamic routing or layer 4 connection load balancing, all these are possible. Attack detection and mitigation, as Arvin yesterday from Microsoft said, NFV is great, but sometimes, especially under DOS, you really have to download or offload something to the physical network. Otherwise, right, when the traffic is at the server, it's too late. There is no way you can protect particular tenants if all the traffic have to come to your servers anyway. Post-stack offloading, VM switch, part of the VM switch, especially classification kind of things, are very expensive, so you might want to offload it to the hardware. And also this will affect various types of network devices, not just the switches and NICs and middle boxes. And as you have seen, even software guys like P4, because actually there was a demo yesterday about P4 working as a front end of OBS. And why? Because imagine that you came up with your own new protocol by tweaking OBS code, kernel code or user level code. Now the question is, what if OBS moves on to the next version? Do you have to redo the work? Or maybe another possibility is you write the code, your own protocol, and then you upstream it. but there are only so many people who can actually make this upstream happen through the Linux community. Right? So if there is a unified channel to be able to define new protocols, something like P4, even OBS can benefit from that. This will create lots of significant R&D opportunities, novel network and protocol designs, take advantage of unprecedented amount of visibility and control into the network. Joint design and optimization between host and network. Especially these large online service providers, they already own the end host, either through the virtualization or by running their own applications only. So they can actually introduce a lot of knowledges into the data packets. For example, they can embed application ID. As long as they have, header, as long as they can introduce their own headers, they want to introduce a lot of things into the network. And then based on the application ID, they may actually choose different queues or different paths. Right. So this kind of joint optimization is also very promising. Development tools, compilers, debuggers, static analyzers, profilers, all sorts of people programming assistance tools. We're just starting. We just have very basic compiler and visualization tool, but there are lots of tools that we will need going forward. So contributing to this will be huge impact. Verification, test, and simulation. Right? Now we have unambiguous definition of the data plane behavior that will bring this network verification test, this research project up to the next level. So far you've been doing this only based on rough understanding. Okay, IP routing works this way, so let me grab IP routing table from the control plane occasionally by taking snapshot, and from there you run verification. That's like very second-handed indirect approach. Why can't you just grab it? Why can't you let every single packet carry whichever routing information it was actually used to, right? And then you collect that information and then use it for verification. Many more. And you already know about language consortium. It maintains the new spec. Reference P4 programs, compiler, software P4 switch, test framework, all these are already available. Anybody can join for free. And the reference P4 program, the most extensive one is switch.p4. And then it has these features already implemented in P4. So if you're interested in understanding how these are implemented, go look at this particular program. And then more are coming up. So summary, next few years, data plane programmability will quickly become commonplace. And this will accelerate innovations in networking. Programmability, whenever programmability happens, accelerate. Programmability plus commodity resources always brings in innovation. That's the repeated history of computing industry. No more black boxes in white boxes. And as a common industry-wide forwarding language, P4 will play crucial roles, and then your help on P4 will be appreciated. And lots of R&D opportunities are opening up. So it's right time to join and contribute.